Hello everyone. In this video we are going to study chemical kinetics. Well, kinetics, as the name suggests, it is the study of the rate of some progress. And in chemistry, we deal with the progress of any particular reaction. Therefore, chemical kinetics deals with the rate of the progress of any reaction, or the rate at which any reaction is progressing. We know that the reaction is taking place whenever the product starts getting formed in the reaction vessel, and we also know that it can be seen otherwise as the disappearance of reactants. So we know that the reaction is progressing whenever the reactants are getting disappeared or the products are getting appeared in the reaction vessel. Therefore, the rate at which the products are getting appeared or the reactants are getting disappeared is dealt in chemical kinetics. And we know that rate of something is the derivative of it with respect to time. Okay. Since, for example, we know that velocity, it is the rate of change of distance with respect to time. Okay. And mathematically it is denoted as dx by dt. Therefore, in chemistry, rate of reaction, it is denoted by the change at which the concentration of any reactant or products is taking place. Therefore, in chemistry, rate of reaction is d by dt of concentration. Okay, so suppose any reaction is given to us. This is A plus B. Suppose there is another substance C. Or, currently just dealing with A plus B. It is giving us product P. So, since we have already discussed here that the rate at which the appearance of product is taking place is the rate of reaction. And here the rate of reaction is defined as the d by dt of concentration. Therefore, the rate at which concentration of product is appearing is known as rate of reaction. Therefore, rate equals d by dt of concentration of products. Okay, so with respect to products, we have defined rate as d by dt of concentration of products. But there must be something with respect to reactants as well. Suppose the product is a colorless gas. Therefore, in order to observe that the reaction is taking place or not, we will have to observe the reactants. And hence, rate equals d by dt of reactants as well. Now, since we know that reactants are disappearing in this reaction, therefore concentration of this species A is constantly getting decreased, but rate is always positive. And since d by dt will be negative in this case, because concentration is getting decreased constantly, therefore we will mark here negative sign before d by dt of A, and hence rate is negative of the rate of concentration, the rate of change of concentration of reactants. And this will be equal to disappearance of reactant B, because since A and B are here in equal proportions, therefore rate at which A is disappearing will be equal to the rate at which B is disappearing. Because if 1 mole of A is getting eaten in this reaction, it is reacting with 1 mole or 1 molecule of B. So 1 molecule of A is getting combined with 1 molecule of B. And therefore, the rate at which A is disappearing will be equal to the rate at which B is disappearing. Now here we have discussed here when 1 molecule of A and B is present. Okay, and here it will be equal to d by dt of B using the same argument. Now, what drives that reaction? This must be a question in your mind. Well, a reaction is always driven by collision of molecules. When A and B are colliding with each other, they are giving us products. So there are two theories which drive the chemical kinetics. Two theories. So there are two theories driving chemical kinetics. First theory is known as collision theory, and the second theory is known as transition state theory. Transition state theory. Okay, now collision theory, as the name suggests, it is dealing with the collision of reactant molecules to form a product. So to understand the collision theory, suppose this is a molecule A, this is molecule B, and they are colliding with each other and giving us A, B, or some other compound B. Okay, so this transformation is taking place only when A is coming near to B, and they are coming so much nearer to each other that they are eventually reacting with each other. So since collision is playing an important factor here, therefore we can say that rate should be equal to the speed of the collision. Okay, so it must be equal to the mean speed of A or B, because the faster A and B collide to each other, the faster the product formation will take place. Therefore, rate must be directly proportional to the speed of the molecules. And since we know that here mean speed is directly proportional to under root temperature by molecular weight, therefore this implies that rate should be directly proportional to the temperature and molecular weight, T by M per half. Okay. Now further, it is observed that the amount of molecules that have got a minimum amount of threshold energy, we call it threshold energy. So the amount of molecules that have got minimum amount of energy, they undergo only transformation. So there is a particular amount of energy barrier, so that is known as EA, and this is the ground state known as EG, and this is the energy barrier known as EA, or activation energy. If we draw the progress of any reaction here, and there is energy on y-axis and reaction coordinate on x-axis, then reaction takes place like this, in this manner. This is the energy of reactants, this is the activation energy, and this is the energy of products. Here we call delta H as ER minus EP. Okay, delta H of this reaction. So therefore, in order to reaction occur, there must be a minimum amount of EA present in each and every molecule so that they can get transformed into products, and hence the rate of reaction is directly proportional to the fraction of the molecules that have got minimum amount of energy as EA, and that fraction is e raised to the power minus EA upon RT. So we can say that from here rate is directly proportional to T by M to the power 1 by 2 e raised to the power minus EA upon RT, and rate is directly proportional to the concentration of A and B present, because the more concentration of A and B present, more will be the rate, and hence this is directly proportional to the concentration of both of the species. Okay. Now, collision theory also states that in order to have collision and the product formation, the collision must be effective. And by effective collision, we mean that here there is some reaction sites present here. So if any A and B molecules are colliding with each other, then they must have proper orientation in order to transform into products. We will discuss this in detail later in Arrhenius equation, but here just understand that there must be a proper orientation of product formation so that they can have the collision as effective. So suppose 100 collision is taking place, therefore not all the collisions must be having proper orientation. We know this. Therefore there is a factor known as P, which signifies us that not all the collision are effective, only a factor of collision is effective. Therefore this amounts for effective collision. Effective collision. This is for energy. This is kinetic energy, in fact, kinetic energy part. And this is the activation energy part, or minimum energy. Minimum energy part. Okay, so taking all taking all these concepts in mind, Arrhenius developed an equation known as A, which is a constant factor, and it takes care of all these factors that are coming into this equation, rate of equation, and e raised to the power minus e A upon R. The concentration of A and concentration of B. So this factor is known as rate constant, K, rate constant. So this factor is known as rate constant of any particular reaction. Therefore, from here we can say that rate equals rate constant into concentration of species involved in this particular reaction. So if we have a reaction to us A plus B giving us products, its rate will be rate constant into A into B, as we have already discussed here. So now if the stoichiometric coefficients of A and B are different, suppose the reaction is AA plus B giving us C, or C small c into C. So if the stoichiometric coefficients of the species are different, then we will then it was examined that the rate of appearance or the rate of disappearance of A was A times the rate of that particular reaction. So it was observed that if A is giving us CC, or suppose first examining this reaction, A is giving us B. Example to us is 2N giving us N2. Suppose this is a hypothetical equation. So if A stoichiometric is small a is the stoichiometric coefficient of capital A, that is compound A, and small b is the stoichiometric coefficient of compound B. So it was found that the rate of reaction or disappearance, rate of disappearance of reaction minus dA by dt was A times rate of reaction, and rate of appearance of products was B times the rate of reaction. Therefore the rate at which the reaction is progressing was 1 by A time or 1 by B time of the rate at which that particular species is appearing or disappearing. And hence from here it was rate of reaction, since rate is always equal whether we are considering reactants or products. Therefore rate of reaction was 1 upon A times the rate of disappearance of A, and it was 1 upon B times the rate of appearance of B. Okay, this is the concentration drop. So from here we can say that the rate equal in this reaction AA plus B. Suppose this is the reaction giving us a C into C of AB. Suppose this is the reaction then rate equals 1 upon A minus dA upon dt equals 1 upon B minus dB upon dt equals 1 upon C d by dt AB. Hence from here we can say that rate or R equals 1 upon A minus 1 upon A dA upon dt equals minus 1 upon B dB upon dt equals 1 upon C dAB, here it is AB, dAB by dt. Okay, so the other theory was transition state theory, and for this you do not need to go deeper into this section because this is not primarily in your course. But remember that in transition state theory, the transition state or the intermediate formed in the reaction is more stable than the reactants, and that is what driving us to the products. So in this case, transition state theory, suppose A plus B, or suppose AB plus C is there. It is giving us first A, and this bond is getting broken, B, and this new bond is getting formed, C. So this is giving us A plus BC. In this case, this is the transition state which cannot be isolated, but this is more stable than this state is more stable than the reactants, and when this state reaches, when this transition state is reached, then in order to achieve minimum energy level, or in order to achieve more stability, this is getting transformed into products here. See, in this reaction coordinate, this forms us the transition state. So when that activation energy is reached, a transition state is formed which is more stable to these reactants, and this is driving us to the products. Here the pre is getting formed, that is products, and here is the reactant, and here the transition state is getting formed, which is not isolated. Okay, so this is the transition state theory, although you do not need to go into much detail of this theory because this will lead to quantum mechanics or quantum dynamics. So now suppose any reaction is given to us, A plus B giving us CC plus D of the species. Now mathematically, rate of chemical reaction will be rate equals minus 1 upon A d by dt of A. It will be equal to minus 1 upon B d by dt of B. It will be equal to 1 upon C d by dt of C, or 1 upon D ddt of D. Now we have used here negative sign because in case of reactants, as the reaction progresses, reactants are disappearing. Hence the concentration of species A and species B are getting decreased. Therefore we have used here negative sign to compensate for that decrease in concentration of the reactant species, and no negative sign has been used to signify the appearance of the concentration of species C and species D, because they are appearing, hence their concentration is continuously increasing. Therefore no need for the negative sign for these species. Now the rate of chemical reaction has got unit as mole per liter per second. So their its unit is mole per liter per second, and or mathematically in other form, the rate of chemical reaction is proportional to the product of effective concentrations or active masses, to be more precise, of the reacting species, each raised to the power that is equal to the corresponding stoichiometric number of substance appearing in the chemical reaction. Therefore, in this case, rate will be denoted more specifically as K, the concentration of A to the power A, concentration of B to the power B, where K is the proportionality constant known as the rate constant for this particular reaction. But experimentally it has been observed that this equation is not always applicable. Therefore, in general, rate equals K into concentration of A to the power A dash into concentration of B to the power B dash, where A dash and B dash may or may not be equal to A and B respectively. And also, A dash and B dash, they can be negative, they can be positive, or they can be zero also, or even they can be fractional. So the quantity A dash plus B dash, it is known as the order of reaction, where A dash is the order of this reaction with respect to species A, and B dash is the order of this reaction with respect to species B. Okay. Now, where K is the rate constant, or more formally specific rate constant, and the unit of K depends on the value of A dash and B dash. So the unit of rate is always mole per liter per second, and the unit of concentration is always mole per liter. Therefore, modifying their units with respect to A dash plus B dash, we get the unit of K. We'll see it later how do we get the value of K for different kinds of species or for different kinds of reactions. Now, always remember that order of reaction, that is A dash and B dash, they cannot be found by looking at stoichiometric coefficients. It is entirely an experimental process. So, now in this case, we assume certain things. To derive this particular expression, we have assumed some things. Now let's see what assumption that we have taken. The assumption is the reactants are not pure solids. Reactants are not pure solids. Another assumption is that they are not pure liquids. Reactants are not pure liquids. And there is one more assumption, and this is that the reactants are not in excess. Reactants are not in excess. Now this is the case because concentration equals moles per unit of volume equals moles upon volume. Right. Now, if the reactant is pure solid or if the reactant is pure liquid, then we can modify this expression as moles equals mass upon molecular weight upon volume is mass upon density. Okay. Now the density of pure solid and pure liquid does not change. So this quantity becomes density upon molecular weight, which is a constant term. Hence, whatever species which are in their pure solid or pure liquid form, we do not consider them in the expression of rate constant, or in the expression of rate law, that is known as rate law. Okay. So, in this case, rate law becomes, suppose the reactant A, suppose the rate law is rate equals K into A into B. Now suppose A is pure solid, or it is pure liquid, or it is in excess. Then we can write rate constant as K dash into B. Because here K dash equals K into A, and since A is constant, K is constant, it gives another constant term. So if the reactant is in excess, then whatever change in reaction takes place, they are not apparently affecting the concentration of A species, and hence whenever any species is in excess, it is also not considered in the rate law. Okay. So in this case, order with respect to A may be interpreted as 0. Now, let's study about integrated rate laws. Integrated rate law for first order reaction. For first order reaction. Okay, now in case of first order reaction, suppose the reaction is taking place via this process A plus B giving us C. Now suppose the reaction is first order with respect to A and 0 order with respect to B. Okay. So in this case, rate law is R equals K A. Fine. Now this equals minus dA by dt. Okay. So if we simplify this further, we get something like K into dt equals dA upon A with minus sign. Therefore, simplifying it further, we get an expression. This says that ln A, concentration of A, and A naught, that is initial concentration of A, upon ln upon concentration at time t equals kT. Therefore, ln initial concentration of A upon concentration at time t equals kT. So this is the expression for first order reactions. This is known as integrated rate law. So suppose the species are in their gaseous forms and it has got initial pressure as P naught and pressure at time t as Pt. So if the species are in gaseous form, then integrated rate law can be written as ln P naught upon Pt equals Kt. Okay, so suppose we have calculated the rate for any particular reaction at T1 and T2, and we have got the value of concentrations as AT1 and AT2, then this law can also be written as ln concentration of A at T1 upon ln concentration of A at T2 equals K into T2 minus T1. Okay, we have done here nothing. We have just equated ln A naught terms for both of these conditions. So, simplifying this further, if we simplify it further, we get value of A at particular time. Sorry. Now, if we simplify this further, we get the value of A at particular time t as A naught e raised to the power minus kt. And this is known as Wilhelm's equation. Okay, so from here, if we put the value of At as A naught upon 2, then at particular time t, the concentration of species A is half of that of its initial concentration. So we call that point of time is T of half time, that is half time of a particular reaction. We denote it as T half, and for first order reaction it is 0.693 upon K. Hence from here we can say that the half-life of any particular first order reaction is independent of the initial concentration of that particular reactant. So in case of first order reaction only, half-life is independent of the initial concentration of the reactant. So if we generalize this term, then half-life of an nth order reaction, the half equals 2 raised to the power n minus 1 upon n minus 1 a naught to the power n minus 1 to kn. So this is the generalized equation for nth order reaction for half-life of any reaction. So now this apparently at first sight it may seem that this equation is not valid for first order reaction, but this is not true. This equation is valid for first order reaction as well, but you have to do a little bit of mathematics of limits and derivatives here, although you do not need to go into that intricacies. So from here we get the conclusion that half-life of any particular reaction is inversely proportional to the initial concentration of any species raised to the power n minus 1. So therefore, we can say that there will be different half-lives for two different initial concentrations for all reactions other than first order reaction. Okay, so in case of first order reaction, there will be a single half-life irrespective of the initial concentration of that particular reaction. Okay, now there are a type of reaction known as parallel reactions. So in case of parallel reactions, two products are formed from same set of reactants by different paths. Okay, and these are also known as simultaneous reactions. Suppose reactant A is giving us B with rate constant K1, and it is giving us C with rate constant K2. Okay, so now let after time t, the amount of B is X and the amount of C is Y after time t. Okay, so here rate of disappearance of A, that is minus dA by dt equals K1 concentration of A plus K2 concentration of A. K1 concentration of A plus K2 concentration of A. Or this equals K1 plus K2 concentration of A. Now, if we simplify it further, or we can write it in other form, that rate of appearance of B, dB by dt equals K1 to the concentration of A, and the C by dt equals K2 into concentration of A. Now, if we simplify these equations further, we get something like X upon Y equals K1 upon K2. So therefore, the ratio at which they will be deposited after time t will be equal to the ratio of their particular or their respective rate constant. Or being more precise, it is known as specific rate constant. Okay. Now let's study about effect of temperature on reaction rate. Yes, temperature do affect the reaction rate, and the temperature coefficient is the ratio of rate constant of a chemical reaction at two temperatures differing by 10 degrees Celsius. Okay, and now at particular increase of 10 degrees Celsius, the rate of reaction increases by a factor of 2 or 3. Okay, now therefore temperature coefficient it equals rate constant after the 10 degree increase in temperature divided by rate constant at temperature T. Okay, now this value generally comes in between 2 23. Therefore, we can say that the rate of reaction becomes twice or thrice with every 10-degree increase in temperature. Now, actual dependence of rate constant on temperature is represented by Arrhenius equation. Okay, and now Arrhenius equation states that rate constant equals A e raised to the power minus EA upon RT. This is known as Arrhenius equation. Okay, now what do these two different terms tell us? It is that A, the factor A is telling us the total number of effective collisions, total number of effective collisions, okay, and this expression, another expression, it tells us total number of collisions that have sufficient amount of activation energy, okay, that have sufficient activation energy. Okay, so to understand this equation, we need to go to the theory of collision of the molecules to complete any particular reaction. We call it as collision theory of any reaction. Now, collision theory states that suppose there are two molecules, molecule A and molecule B. In order to react, firstly they need to collide. Yes, we all know that collision occurs. That's why a reaction takes place. Okay. Now, if the collision does not occur, reaction will not occur, and hence to make a product C, they will have to collide. Now, the thing that matters is how are they colliding. Okay. Suppose the reaction site for B is here and reaction site for A is here. Now, if they collide in this manner, it will not be any effective collision. Okay, so this collision means nothing. The collision that means something is if A has got reaction site here, B has got reaction site here, and now if they are colliding, that means that okay, now the reaction is taking place. And also there is another condition, and it is that all of them, that is their molecule A and molecule B, they must have the minimum amount of activation energy in order to proceed further in forming a product. Okay, so this is told by this expression, in which this term e raised to the power minus EA upon RT tells us the fraction of molecules, or the total number of molecules that have sufficient activation energy, and A, it is telling us total number of effective collisions. Therefore, reaction sites are dealt with A, and the molecules that has minimum amount of activation energy is dealt with E. Okay, now A is known as Arrhenius constant or free exponential factor or frequency factor, you can call it anything, and EA is known as activation energy. Okay, now if we solve it further, we get an expression which looks like log K equals log A minus EA upon 2.303 R. Okay, now if we plot a graph between log K and 1 upon T, this is log K and this is 1 upon T. Okay, we will get a graph which looks something like this. And the slope has the value minus EA upon 2.303 RT. Therefore, we can find the activation energy of any process by plotting a graph between log K and 1 upon T. Now, if we compare the values of K at two different temperatures, suppose T1 and T2, then we will get two different values known as K1 and K2, and they are related by formula log K2 upon K1 equals EA upon 2.303 R 1 upon T1 minus 1 upon T2. Okay. Now there is another branch, another small branch in chemical kinetics itself. It is known as radioactivity. Remember that all radioactive decay follows first order reaction, and hence every concept is same in case of radioactivity. Okay, so here you can say that all radioactive decay follows first order reaction. Okay, suppose any decay is taking place where A is getting transformed into B, then we can write as minus dNA by dt equals lambda NA, where lambda is similar to the rate constant known as decay or disintegration constant. NA is the number of nuclei at a given amount of time. And here, just like first order reaction, T half equals 0.693 upon lambda. And here there is another new term known as T average. T average equals 1 upon lambda. Okay. Now there is similar to first order reaction. Since in first order reaction we dealt with the concentration of any species, here we are dealing with the number of molecules of that particular species or number of nuclei. Therefore, just like first order reaction, concentration will get replaced to number of nuclei, and hence ln n naught upon nt equals lambda t. And now, considering this T half and T average expression, we can say that T average or mean time equals 1.44 into T half time. Okay. Now, there is a term known as activity, and the activity of any radioactive element is the rate at which it decays. Okay. Now, activity is given by A equals lambda n. Okay. Therefore, at time t, activity equals A naught e raised to the power minus lambda into. Okay. Now, it is different from dNA by dt. Here, minus dNA upon dt, it describes the rate of change. It describes the rate of change, whereas A describes the rate of decay. It describes the rate of decay. Okay, so activity is different from d and A by dt. Okay, now since here you have seen that minus d and A by dt equals lambda and A, and here A equals lambda n, but their meaning are different. So the amount of since this is a first order reaction, hence we can say that the amount of radioactive substance left after n half-lives, radioactive substance left after n half-lives equals A naught upon 2 raised to the power n. Okay, so remember that any radioactive decay, it is following first order reaction always. Now let's discuss some of the questions. Now the first question, it says that the gaseous reaction A getting transformed into 2B plus C is observed to be the first order. On starting with pure A, it is found that at the end of 10 minutes, the total pressure of the system is 176 millimeter of Hg, and after a long time it is 270 millimeter of Hg. Now calculate A, the initial pressure of A, the partial pressure of A after 10 minutes, and C, the rate constant of the reaction. Okay. Now let's solve the first part of this particular problem. It is asking us to calculate the initial pressure of A. Now let the initial pressure of A be P0 millimeter of Hg and the pressure of A decreased in 10 minutes be A. So let the initial pressure of A be P0 millimeter of Hg and the pressure of A decreased in 10 minutes be A. Okay, so hence we can write the reaction which looks somewhat like this. A giving us 2B plus C. Therefore, initially it has the pressure P0 and they have zero pressure, and at time t, at time 10 minutes, it has a pressure P0 minus A and their pressure is 2A and A, and at time infinite, which is infinite, the pressure of A is 0, pressure due to B is 2P0 and this is P0. Now after long time interval, total pressure equals 2P0 plus P0 equals 3P0. Okay, now it is given that P infinity equals 270 millimeter. Therefore, P0 equals P infinite upon 3 equals 270 upon 3 equals 90 millimeter of Hg. Here we were supposed to calculate the initial pressure of A. So the initial pressure of A comes out to be 90 millimeter of Hg. Okay, so now let's see the second part of this problem. Second part, it is now after 10 minutes, let pressure is Pt. Pt equals P0 minus A plus 2A plus A. Here, the total pressure will be P0 minus A plus 2A plus A. So it will be P0 plus 2A. Now it is given that the pressure after 10 minutes is 176 millimeter of Hg. So therefore this implies that 176 equals 90 plus 2A. So from here we get the value of A as 43 millimeter Hg. 43 millimeter of Hg. Okay, so now from here, since we have got the value of A, we know the value of P0. Therefore, partial pressure of A after 10 minutes equals P0 minus A equals 90 minus 43 equals 47 millimeter Hg. Now, the last part is asking us to calculate here. The last part is asking us to calculate the rate constant of the reaction. Now, for the first order reaction, the rate constant expression for first order reaction the rate constant expression is K equals 2.303 upon T log initial pressure by pressure at time T, that is P0 minus E. Okay, so from here we get the value of K as 2.303 upon 10 log 90 upon 47. So from here value of K is 0.0649 per minute. Okay, so we have got the value of rate constant as asked in the question. The unit will be per minute because this is the SI unit of the rate constant, which is time inverse. So the here it was given in question after 10 minutes. It was given already. It was given in question. So we have calculated the unit of rate constant as 0.0649 per minute. So let's come to another question. The question says that it is an example of that simultaneous reaction that we studied just now. It says that A is giving B and C simultaneously with rate constant K1 and K2 respectively. The value of K1 is A per R and K1 ratio K2 is 1:10. Calculate concentration of C by concentration of A after 1 hour from the start of the reaction, assuming only A was present in the beginning. Okay, let's approach this problem. Here, since this is a simultaneous reaction, therefore we can write the value of rate as solution. There, since this is a simultaneous reaction, therefore minus dA by dt equals K1 plus K2 A. Okay. Now, if we separate the variables from here, we get minus dA upon A equals K1 plus K2 dt. Now, if we integrated this expression and if we solve it further, we get the value of this like ln A naught upon AT equals K1 plus K2 into T. Now, since it is given, since concentration of B upon concentration of C equals 1 upon 10, it is given in the question. Therefore, we can write that concentration of A. Okay, we'll do it later. So, and now since A naught at any particular instant, the total concentration will remain same. Therefore, at A naught will be equal to concentration of A at time t plus B plus concentration of C. Now, therefore, ln A at time t plus B plus C upon A at t equals K1 plus K2 into T. Now, from here, if we simplify it further, we get ln 1 plus, since B equals C upon 10, therefore C upon 10 plus C divided by AT. Okay, AT. It comes out to be 11A. Okay, so since K1 equals A per R, therefore K2 equals 10A. So K1 and K2 will be 11A. Okay. So and time, it is already given in the question. We have to deal with time equals 1 hour. Therefore, substituting t equals 1, K1 and K2 as A and 10A respectively, we get K1 plus K2 into T as 11A. Okay, so from here we can say that ln 1 plus 11 upon 10 C upon A T equals 11A. So from here the equation can be written as, if we simplify it further, this equation can be written as C upon A equals 10 upon 11 e raised to the power 11a minus 1. So this is the answer that we are looking for. Okay, so let's come to another question. This question is based on radioactivity. We studied just now the radioactivity. The question says that in nature, a decay chain series starts with thorium 9232 and finally terminates at lead 82208. A thorium ore sample was found to contain 8 into 10 raised to the power minus 5 milliliter of helium at STP and 5 into 10 raised to the power minus 7 gram of thorium. Find the age of ore sample assuming that source of helium to be only due to decay of thorium-232. Also, assume complete retention of helium within the ore. Now, half-life of thorium-232 equals 1.39 into 10 raised to the power 10 years. Okay. Now, if we write the reaction involved in this particular question, then the reaction will be written as 90 thorium-232 giving us lead 82208 plus 6, and it gives off helium. And 4 minus 1 is 0 positron. Okay, so therefore 6 into 22400 milliliter of helium is formed by 232 gram thorium decay. Okay, since 1 mole of thorium is giving us 6 moles of helium and 1 mole of any gas occupies 22,400 milliliter at STP, hence we can say that 6 into 22,400 milliliter of helium is formed by 232 gram of thorium decay. Therefore, 8 into 10 raised to the power minus 5 milliliter of helium is formed by 232 into 8 into 10 raised to the power minus 5 upon 6 into 22,400, and now this is into gram thorium decay. Okay, so therefore from here we can say that this amount of helium is formed by 1.38 into 10 raised to the power minus 7 gram thorium decay. Now at time t, sample has 5 into 10 raised to the power minus 7 gram of thorium. Okay. Now at time t, sample has 5 into 10 raised to the power. At time t, sample has 5 into 10 raised to the power minus 7 gram thorium. Okay. And at t equals to 0, sample has 5 into 10 raised to the power minus 7 plus 1.38 into 10 raised to the power minus 7 gram thorium. So from here it has 6.38 into 10 raised to the power minus 7 gram thorium. Okay, so from here the value of T equals 2.303 upon K log n naught upon nt, since we know it from the rate equation of radioactivity. So from here the value of T is 2.303 upon 0.693 into 1.39 into 10 raised to the power 10, because T half equals 0.693 upon K, hence K becomes 0.693 upon T half. So substituting that expression here, this becomes equal to T becomes equal to 2.303 upon 0.693 into 1.39 into 10 raised to the power 10 log 6.38 into 10 raised to the power minus 7 upon 5 into 10 raised to the power minus 7. Okay, so from here time comes out to be 4.89 into 10 raised to the power 9 years. Okay, so this is what was asked in this question. Now, there is another question. The question says that for the reaction 2NO plus H2 gives us N2O plus H2O, the value of minus dP by dt was found to be 1.5 torr per second for a pressure of 359 torr of NO and 0.25 torr per second for a pressure of 152 torr. Now the pressure of H2 being constant. And on the other hand, when the pressure of NO was kept constant, minus dP by dt was 1.60 torr per second for a hydrogen pressure of 289 torr and 0.79 torr per second for a pressure of 147 torr. Determine the order of the reaction. Okay, let's find out what we do get. Now for a given reaction, the rate law, suppose the rate law is represented as minus dP upon dt equals rate equals K P NO A P H2 B. Let the order of reaction with respect to NO is A and the order of reaction with respect to H2 is B. Therefore, overall order of the reaction is A plus B. Okay, now using the date given in the problem and now keeping the pressure of H2 constant, we get 1.50 equals K into 359 to the power A pressure to H2 to the power B, and 0.25 equals K into 152 to the power A pressure due to H2 to the power B. Now since they are constant, they are same. If we divide this expression by this, we get 1.50 upon 0.25 equals 359 upon 152 to the power A equals 6. It is given in the question. This is equals to now 6, since 1.50 by 0.25 equals 6. So 359 by 152 to the power A equals 6. Now taking log on both sides, log 6 equals A of log 359 upon 152. So from here we get the value of A as 2. Therefore, order of reaction with respect to NO is 2. Now similarly, by keeping the pressure of NO constant, the law should be keeping the pressure of NO constant. In this case, 1.60 equals K PNO and 289 to the power B. Here 0.79 equals K PNO to the power A 147 to the power B. Now if we divide this expression with this one, we get 1.60 upon 0.79 equals 289 upon 147 to the power B. Okay, so here if we take log at both sides, we get log of 1.60 upon 0.79 equals B into log of 289 upon 147. So solving this expression, we get the value of B equals 1. Therefore, order of reaction with respect to H2 is 1. And hence, therefore, overall order of the reaction equals A plus B equals 2 plus 1 equals 3. So this is the answer. So let's discuss another question. The question says that a hydrogenation reaction is carried out at 500 Kelvin. If the same reaction is carried out in the pressure of a catalyst at the same rate, if the same reaction is carried out in the presence of a catalyst at the same rate, the temperature required is 400 Kelvin. As we know that presence of catalyst, reaction gets accelerated. Okay, now calculate the activation energy of the reaction if the catalyst lowers the activation barrier by 20 kJ per mole. Okay, so let's see what is the Arrhenius equation in both of these cases. So according to Arrhenius equation, K equals A e raised to the power minus E A1 upon R T1. It is at 500 Kelvin and the absence of catalyst. Okay, now K equals A e raised to the power minus E A2 upon R T2. This is at 400 Kelvin and presence of catalyst. Both of these quantities are same. Therefore, e raised to the power minus E A1 upon R T1 equals e raised to the power minus E A2 upon R T2. Here, because K in this case and K in this case, they are same. Okay, so therefore this is the case, and hence from here EA upon R T1 equals EA upon R T2. Okay, now let activation energy of reaction in absence of catalyst be EA1 and in presence of catalyst it is lowered by 20 kJ per mole. So let activation energy of the reaction in absence of catalyst is EA. So therefore from here it is EA1, here it is EA2. So from here, therefore in the presence of catalyst, that activation energy becomes E dash A. In the presence of catalyst. Oh, sorry. Here we have already described. We have already assigned the variable for activation energy. So activation energy in the absence of catalyst is EA1, and in the presence of catalyst it is EA2. So therefore EA2 equals EA1 minus 20, and hence EA1 minus 20 upon 400 equals EA1 upon 500. So if we solve this expression further, we get the value of A1 equals 100 kilojoule per mole. So therefore the value of activation energy in the absence of a catalyst is 100 kilojoule per mole. Okay. Now let's discuss another question. And the question says that a mixture of Pu-239 and Pu-240 has a specific activity of 6 into 10 raised to the power 9 dps. The half-lives of the isotopes are 2.44 into 10 raised to the power 4 years and 6.58 into 10 raised to the power 3 years respectively. Calculate composition of the mixture. Now let the total mass of sample be 100 gram. So let the total mass of the sample, equals 100 gram. So therefore their respective masses will be so first let's consider So let's consider and let the mass of Pu, this is a gram. Therefore, mass of this species, will be 100 minus a gram. Now, total activity of the sample will be the sum of the activities due to both of these constituting species. Okay. Therefore, total activity of the sample equals activity due to this activity due to 239 plus activity due to 240. Okay, and hence from here the specific activity of sample into total mass of sample will be activity due to both of these species. So the total activity will be specific activity into total mass, and hence we can write as 6 into 10 raised to the power 9 into 100. 6 into 10 raised to the power 9 into 100, because here it was given to us that specific activity was 6 into 10 raised to the power 9 dpl. Therefore, total activity will be specific activity into mass of sample. So 6 into 10 raised to the power 9 into 100 equals A into 6.023 into 10 raised to the power 23 upon 239 into 2.44 into 10 raised to the power 4 into 3.15 into 10 raised to the power 7 plus here it will be 100 minus a, amount is 100 minus a into 6.023 into 10 raised to the power 23 upon 240 into 6.58, that is half life, into 10 raised to the power 3 into 3.15 into 10 raised to the power 7. Okay, so from here if we solve this expression completely, we will get the value of A as 69. Therefore, the respective percentage will be percentage of 239 is equals 60 equals 69%, and percentage of this is 100 minus 69 equals 31%. This was what we were supposed to find out. So let's discuss another question. Now the question says that A follows first order reaction. A is giving us product, so the rate of reaction with respect to is K into A, and the order of reaction with respect to A is 1, and A follows first order reaction. Concentration of A changes from 0.1 molar to 0.025 molar in 40 minutes. Okay. Find the rate of reaction of A when concentration of A is 0.01 molar. So we can see that concentration of A at time t is 1/4 of that of its initial concentration, and hence we can say that in this case when half-life is reached, the further half-life, that is it takes total of 2 half-lives to get the concentration to 1/4 of that of initial value. Therefore, here time equals 2 into t half. Okay, so hence we can say that and now since it is written that 2 into t half equals time equals 40 minutes, so therefore from here half-life equals 20 minutes. Okay, since half-life is 20 minutes and we know the value of K equals 0.693 upon t half, So it comes out to be 0.693 upon 20 per minute. So therefore rate equals K into concentration of A. Concentration of A is given to us as 0.01 molar. So from here rate equals 0.693 upon 20 into concentration of A into 0.01. So the rate comes out to be 3.47 into 10 raised to the power minus 4 mole per liter per minute. Okay, so now let's come to another question. Well, that previous question, it was asked in IIT JEE. It was asked in IIT JEE 2004. So this question was asked in IIT JEE 2004. Paper was screening paper. Okay, so let's come to another question. Question looks like this. Now 2x giving us 3y plus 2z. Now time in minutes was plotted with partial pressure of x in millimeter of Hg. Now time initially, that is at 0 time, partial pressure of x is 800 millimeter of Hg. At time 100 minutes, partial pressure of x is 400 millimeter of Hg, and at 200 minutes, the partial pressure of x is 200 millimeter of Hg. Now assuming ideal gas condition, calculate order of reaction, rate constant, time taken for 75% completion of reaction, and total pressure when Px equals 700 millimeter. Now by the given data we can assume we can observe. Now since reaction is in this case 2x giving us 3y plus 2z. Okay, now since if we observe the given data, we can say that T half of x is constant. So T half of x is 100 minutes. Okay, since the partial pressure of x is 800, it goes to 400 millimeter of Hg in 100 minutes. So partial pressure gets half in 100 minutes. Now further 100 minutes, partial pressure gets further halved. Okay, so therefore we can say that T half of this reaction is 100 minutes. Now we by observation we can say that T half equals 100 minutes. Now therefore order of reaction is 1, because T half is constant. It is not dependent on concentration of x or the pressure of x at a particular instant. As again, just observe it, after 100 minutes T half gets halved of its initial value, and now after further 100 minutes further 100 minutes, partial pressure gets again halved to that of value at T equals 100. So therefore half-life of this reaction does not depend on the partial pressure of x at any time. So therefore in this case the first part has been solved. Now second part, rate constant. Since this is a first order reaction, therefore rate constant K equals 0.693 upon T half. It comes out to be 6.93 into 10 raised to the power minus 3 per minute. Okay. So now time taken for 75% completion of reaction. Now 75% completion of reaction means that only 25% of X is left here. Okay. Now time taken here in this case, time taken for 75% completion of reaction. Now it means that only 25% is left, that is 3/4 gets consumed. Hence now observe that after first half-life 50% of X gets consumed. After second half-life 50% of that 50% left gets consumed. That is 25% of initial value gets consumed. Hence, after two half-lives, 75% of the reactant gets consumed, and hence we can say that 75% of the reaction has been completed. Therefore, time taken for 75% completion of reaction is 2 into T half equals 200 minutes. Now, in chart also you can see that initial partial pressure was 800 millimeter of Hg. Now, after 200 minutes, 200 millimeter of Hg was present. Therefore, we can say that only 25% of the initial value of Hg is present, and hence 75% of reaction is completed at T equals 200 minutes. So the solution of this part of the problem was given in question itself. Okay, so let's come to another part of this question, that is D part. Now here 2x is giving us 3y plus 2z. Now initial pressure here was 800, here 0, 0. At any time pressure is 800 minus x. Here it is 3 by 2x, and here it is x. Okay, now total pressure equals 800 minus x plus 3 by 2 x plus x. So here total pressure is 800 plus 3 by 2 x. Now it is given that 800 minus x equals 700 millimeter. Therefore 800 minus x equals 700. So from here value of x is 100 millimeter He. So from here we get the total pressure as total pressure equals 800 plus 3 by 2 into 100 equals 950 millimeter Hg. So this is the answer of this last part of this problem. And this question was asked in IIT JEE 2005. IIT JEE 2005. This was the subjective question was asked in mains. Now let's discuss one more question, and this is the last question of the video. Now the question is saying that for the given reaction A plus B giving us products, following data were given: initial concentration of A, initial concentration of B, and initial rate. When initial concentration of A was 0.1, initial concentration of B is 0.1, they are in mole per liter, and initial rate is in 0.05. It is in mole per liter per second. They are in mole per liter. This is also mole per liter. So this data is given to us. Now it is asking us to write the rate equation and calculate the rate constant. So let's solve this first part of this problem. Let's discuss how this can be solved. Now let the order with respect to A and B are x and y respectively. Let the order with respect to A and B are x and y respectively. Okay, so therefore rate equals k, that's rate constant, into A to the power x into B to the power y. Okay, now let's observe this part. 0.1 molar of A, 0.1 molar of B, and 0.05 mole per liter per second is the rate. So substituting this first value, we get 0.05 equals k into 0.1 to the power x into 0.1 to the power y. Okay, now observe this middle value, 0.2, 0.1 and 0.1. So substituting this, 0.1 equals k into 0.2 to the power x into 0.1 to the power y. Or from here, now if we divide these expressions. So from here, if we divide this, if we let this is second, let this is first. So dividing second by first, we get 2 equals 2 to the power x. So from here, we get the value of x as 1. Now, observe the third reading, this reading that we are given to us. So 0.05 equals k into 0.1 to the power x into 0.2 to the power y. Okay, let this is third. Now dividing third by first, we get something like 1 equals 2 raised to the power y. So from here, value of y equals 0. Therefore, order of reaction with respect to A is 1 and with respect to B is 0. Therefore, overall order of reaction is 1. Okay, and hence the rate equation is therefore rate equation R equals K into A to the power 1 into B to the power 0. Or to simplify it further, we can write rate equals K. Okay. Now, just observe one of these values, that where rate equals 0.1 and the concentration of A is 0.2, that is this. We can observe any of the values. So let's take this value, this middle value. So from here, we can write rate as 0.1 equals K into 0.2. So from here, value of K is 0.5 per second. Okay, so this is solved. It doesn't matter which observation we are taking. If we would have taken this one also, the value of K would have come the same. Hence, the value of K, that is rate constant, is 0.5%. So this question was also asked in IIT JEE. It was asked in 2004. IIT JEE 2004. So very easy problems are asked in IIT JEE 2000 in IIT JEEs. Well, in JEE, the basic understanding is checked. Therefore, just remember how to calculate the order of reaction from the given data. So nowadays, the question asked are very simple and they are very basic. So keep in mind how to calculate the order of reaction value and how to derive the rate expressions. If you know how to derive the rate equation and if you know the basics, you can solve any question in this